Welcome everyone to the keynote of HIW. It is my pleasure to introduce our invited speaker, Martin Agron. Martin leads a team of quantitative analysts and developers at Standard Chartered Bank since 2008. Previously, Martin worked in related roles at Lehman Brothers, Goldman Sachs, and Credit Suisse. He graduated from London Business School with an MBA in 1995. Martin divided his free time between his children, embedded programming, modular synthesis, and photography and reading history. Today, Martin is going to tell us about Haskell reinterpreted, large-scale real-world experience with the Mu compiler in financial markets. And a final remark, we are going to have questions at the end of this talk. For people on AirMeet, please put questions in the QA tab during the talk, and we are going to go over them at the end. Or you may raise your hand at the end, and we will bring you to the stage so you can ask the questions. With that, please take it away, Martin.
Okay, hello, and thank you for inviting me to speak at this forum. My name is Martin Agron, as you said, and I work at Standard Chartered Bank in Singapore. I should mention that I'm speaking here in my own personal capacity and not on behalf of my employer. So in this talk, I'll speak very little about the commercial environment that we work in, and I will focus specifically on the language topic. I'm going to give you a brief overview before going into some detail on why we built our own compiler. Then we'll contrast this with the real Haskell. We'll talk a bit about the compiler implementation and our libraries. Then we cover some code statistics to see the time evolution, distribution of module sizes, and language extensions. And then we finish off with some current research and potential future development for convergence. And then, as Ning said, Q&A will follow at the end. So just briefly on the business context. So our work here goes under the rubric of quantitative analytics. This is a function that large banks maintain in order to have a competitive presence in securities markets. We're based in the front office, so that we have frequent and direct interaction with trading and structuring functions. We are heavy on financial mathematics, meaning stochastic calculus and measure theory. We are convention laden. We have millions of details of market conventions to keep track of. We do a lot of high performance compute, lots of linear algebra, and lots of Monte Carlo simulation. It's an environment, which is fairly fast-paced, fast-changing priorities, and demand for quick turnarounds. So our team, basically the modeling team, is organized with the product and the model development mirroring the corresponding business lines. And then we have resources for core, applications development, continuous integration, project management, and model risk shared across the business lines. So I'm going to start here with a kind of review of the timeline, basically how I came into Haskell. So a long time ago, like 25 years ago, I started working in the financial markets industry. At that time, the use of spreadsheets was commonplace and development required good integration. This meant that we were writing libraries that could be called as add-in functions from, for example, Lotus 123 or Excel. Institutions could go about this in a manner and style of either, I don't care, anything goes, or slightly more principled, like don't mutate anything upstream. So I was lucky enough ending up working for one of the latters. So we had notions of purity and referential transparency, but we didn't use that terminology. We weren't even familiar with the concept. But that's how we programmed. After that, I guess around 2004, I moved to an institution with almost no spreadsheets, and all the higher level code was written in in-house dynamically checked language. And by 2006, I'd been around in a few different financial institutions, and I wanted to pull together some of the lessons that I had learned. It may not be everybody's lesson, but this was kind of my take on it. And those lessons in summary would be that having a high-level scripting language with an interactive top level is a good thing. Static typing is necessary for development at scale. Purity is required to play well with spreadsheets. And then I was wondering if it would be possible to get some control over effects, even though I didn't really know what that would mean. Now, the answer, of course, is obvious to everybody here in this audience, and that is Haskell. So that's basically how this whole thing started. So from around 2007, I started leading teams that had Haskell, not perhaps centrally in what they were doing, but at least it was an important element. So from 2007 to 2009, we mostly got away with using Haskell as a specification language and for implementing tools. At one of the banks, we were expressly not allowed to have Haskell binaries in production, but we could use it in the development environment. But from 2008, basically since I joined StanChart, we gradually got more adventurous and started using Haskell for a few production packages, as well as widespread use in the development environment. Then by 2009, we had a high demand to deliver scripting capabilities for end users. And our response was to develop a dialect of Haskell that would mesh well with the rest of our ecosystem. And therefore, we made Mu. And basically, since then, there's been no looking back. So why would we build our own compiler? Well, as I mentioned on the previous slide, Haskell was kind of well supported and motivated in the team. That choice wasn't contested, but we had our own ecosystem, and we had an ecosystem and a runtime that already supported code mobility. So what I mean by code mobility? Well, the idea is that you can construct an arbitrary term here, evaluate it in place, or send it over there for evaluation now or later. Over there, that might be a different machine, different architecture, different OS, even different word sizes. And we had built all that functionality during the preceding years, and it formed the basis for everything we were doing or intending to do with respect to distributed compute. So after consulting with people closer to GHC, we concluded that we didn't have the resources to build a custom GHC backend to target our runtime. So we struck a compromise and decided to implement the minimum viable subset of Haskell 98, and then try to reuse our existing backend as is. So from the start, this was a very speculative development. It was intentionally, high probability that it would fail, that we would abandon it, but we gave it a try. And it was done with very few resources. But it turns out, of course, that Lennart can write a nearly complete Haskell compiler in about 2 weeks. So there we go. So, okay, so what is Mu? Well, it's a whole program compiler for Haskell. It compiles to bytecode with a small runtime interpreter, hence the title of this talk. It has lazy semantics, but a strict runtime. And it has no FFI. So all functions from C++ are called natively. All Mu functions have a C++ type of object I function. C++ can apply any object I function natively, and hence we get seamless calling across the language boundary. So now we're going to go into some of the differences between regular Haskell and Mu. So you can't really write idiomatic Haskell if you have strictness all the way to the top. In the lazy language, of course, programmers are accustomed to writing things like from maybe, error, something, expression. But of course, in the strict language, this will fail every time because the arguments are evaluated before the call to from maybe. So the error is always thrown. But Mu implements some tricks to ensure that such code can be treated as if it was lazy. For instance, the definition of from maybe is annotated with a by name pragma, which means that it's always inlined, and that is, it's treated like a syntax macro. Additionally, the implementation takes care to delay the first argument explicitly. And this means, of course, that when it's inlined, you don't get the same problem with argument evaluation. The desirable consequence is that most of the time, we don't need to think about evaluation order when writing this code. The Mu compiler also uses the liberties of lazy semantics to do some aggressive code motion for performance optimization. For example, we're lifting let clauses inwards to near their usage sites. We're inlining a let clause if it only has a single use. And we can identify common sub-expressions and lifting them into let binding to be evaluated once and then shared. In terms of the semantics, the worst thing that can happen, for example, errors, is that they happen in a different order at runtime or not at all compared to strict implementation. And on top of that, having a strict runtime gives us really good stack traces. So the example here shows the typical head of empty list error that is common in Haskell programs and less common in Mu. And they're notoriously difficult to locate when it happens in Haskell because of lazy evaluation at runtime. The Mu exception shows the full stack trace from the definition on line 17 back through call sites in F, lines 13 and 14, and to the usage of F from main in line 8. But there are some consequences of not having real laziness. So as lazy programmers, we're used to creating compiler-like pipelines as the architecture for solving many problems. For instance, ingesting data from a concrete file format might involve lexing, an initial parse, and then a transformation. So we have the functions lex from string to list of token, parse takes a list of token and gives us either an error or the foreign AST, and then we transform the foreign AST to the local AST. So this is natural. And uses laziness to unroll the lex's resulting token stream on demand as the parser consumes it. But in a language with a strict runtime, the entire original string must be consumed and converted to a list of tokens before the parser gets to see anything. On a large data set, this can lead to some unfortunately large memory usage. So in a very few places, we rewrote our lex and parser combinators to have an explicit lazy channel between them, like you see in the continuation form here. The lexer, instead of producing a list of tokens, produces a single token at a time, paired with a continuation that encodes the suspended reminder of the lexing process. Where the parser combinators within the parse function would previously have peeled items from the front of the token stream, just as list operations, now they can peel only one item from the lex return or invoke the continuation on the residual input stream to get another lex return value. So it turned out that making these very few changes to the lexer and parser combinators, it was sufficient for us to allow us to port a lot of Haskell code based on them with no changes in the actual parsers that use the combinators, and then retain the lazy memory behavior. We also have explicit ML-style laziness, which we use. For example, we had a pretty printing library that we got simply by copy-pasting the Haskell library into Mu, and it seemed to just work for years. Then we noticed bad performance, and we evolved some kind of folklore advice to only use it for small things. Then we came across one use case with a small XML file, a small but deep XML file. And it turned out the original Haskell code crucially depends on laziness for performance in this case. And in Mu, under strict runtime, this became accidentally exponential. But the fix was easy and consisted of just adding explicit laziness to a couple of fields in the doc data type. Another difference between Haskell and Mu is that strings as a list of characters, it's kind of a misfeature of Haskell. It's great for teaching recursion over simple data types, but little else. In Mu, we don't have a cart at all. We don't have it as a data type, only string. And the string type is therefore abstract. You can only use it via the provided API. For example, isUpper applies to whole string, not an individual car like in Haskell. And you can see here kind of the various cases laid out for car. And internally, strings are implemented as C++ understood strings with UTF-8 semantics. This implementation works quite nicely because the representation is compact, like byte string, but indexing operations can be expressed in terms of the abstract UTF-8 character position rather than the byte position. And in general, the complexity of string operations is no worse than they were with lists of car, and in many cases, rather better. Okay, so recursion in Mu is a language extension, and you have to switch it on with the pragma. This is kind of a happy accident with the Mu runtime implementation. Before Mu, there was a library written largely in C++, and all Mu code needs to interact with it. Mu functions are essentially evaluated by a bytecode interpreter, which takes up a single stack slot on the C++ stack. And C++ can call Mu by invoking the interpreter, and Mu can call C++ directly. But this means that any call from Mu to Mu is treated just like another call to C++ function, meaning a frame is added to the stack. We don't have any tail call optimization, so all recursion ends up on the C++ stack, and this is relatively small. So recursion tends to work fine for small examples, but it will blow out the stack as soon as you try something reasonably large. Our solution then is to provide all the usual recursion combinators natively as primitives written in C++. So map, fold, unfold, scan, until, loop, etc., are all written in C++. And because these are higher order, you just pass a Mu function to C++ combinator, and only 2 stack frames are used. There's actually a happy benefit of placing this barrier, that is a compilation error, to the casual use of recursion. One, it nudges developers into thinking carefully about the nature of the recursion to choose the right pattern. And it also means that other developers who later need to maintain the code find it more readable. And there's no need to decode Byzantine recursive implementations only to find out their standard pattern after all. Okay, so Mu, having its own standalone compiler, doesn't get any of the GHC goodies for free. So over time, we have implemented several extensions, most notably functional dependencies, type families, and data kinds. These aren't exact matches of what GHC offers. For example, for type families, Mu only has closed type families. For data kinds, we don't promote data types. Instead, data kinds are open and separate from normal kinds. And some extensions, like CPP and template Haskell, were never implemented. These would interact really weirdly with code mobility, because suddenly you would have to know what runs on what machine. So we're not doing those. And since Mu is targeting our pre-existing runtime, it also limits somewhat what we can do. So for example, our runtime only supports rank 1 polymorphism. This rules out higher rank types and existentials. The latter in turn rules out GADTs. And we have no type classes in our runtime. Definitions are specialized starting at main, which is another reason why we need the full program compiler. So if we look at kind of the extensions that we have, basically our favorite extensions apart from those that we can't have, on the Haskell side, we have 1,794 Haskell modules. And the top extension is that in this category is derived data typable. And that's only here because we're still on GHC 7.8. When we upgrade, that's obviously going to go. And then we have record wildcards, which I can take a minor credit for, as Lennart introduced this in response to my complaints trying to use Haskell in a real-world setting back in 2006. And that list of Haskell extensions kind of tapers off fairly evenly, and there's nothing kind of that stands out, I think. On the Mu side, you can see this massive popularity of record wildcards used in 7,975 modules. Multi-param type classes rank second, And this is really because we use it in defining attributes for our financial products, and we have many of them. So that's why it comes up that high on the list. Recursion is also relatively high on the list, but at 975, you can see that's only used in 4% of our new modules. We have 26,000 of them. So clearly, you can write a lot of Haskell without recursion, explicit recursion. So Mu is a whole program optimizing compiler. So the entire source of all libraries are used on each compilation. So what are the upsides from this? Well, we have some optimization opportunities. There's no need for runtime dictionaries for class instances, and all function calls are monomorphized at the usage site. But to be fair, it's not just optimization. We have to do this monomorphization because we don't have rank 2 types. We also get module synchronization. You can never accidentally link against an old version of a dependency simply because we don't have linkage. On the downsides, well, compile time can be rather long. A typical main module can have more than 2,000 transitive dependencies. Some of the mitigations we have there is with some restrictions on exported types, it's possible to load modules dynamically at runtime. And you can also run a compilation server that keeps an in-memory cache of modules already parsed and type checked to share across multiple compiler invocations. Another feature that we have above Haskell, I would say, is that every runtime value can be serialized. So that includes functions. So you can save any partially applied computation and restart it on another machine, even across Windows, Linux, and network boundaries. This enables process-based parallelism across architectures. So ParMap or parallel map is one of our most used facilities. We perform hundreds of thousands of core hours of parallel cloud compute every day of the week. And how do we implement this? Well, so primitive values are just themselves. C++ data constructors have unique IDs plus their internal fields. And we have a versioning scheme to ensure that any old version of a value can be read with a deserializer for a new version defaulting any new fields. C++ runtime functions have stable and unique IDs. And mu functions are a data value of object I function containing the bytecode. And then finally, mu algebraic data types become either enumerations or records in this environment. So this thing that I called code mobility, I consider really the most valuable aspect of the new environment. You can author fresh code from your desktop anywhere in the world and immediately run it distributed on off-premise cloud infrastructure, harnessing tens of thousands of compute cores without any deployment. Another feature that we have that you don't see in Haskell is this notion of SafeIO. So we have SafeIO and IO. Why two? Well, this was initially motivated by the need to get external market data into spreadsheets. Forcibly recalculating, for example, a spreadsheet cell that performs a SafeIO term could bring in fresh market data from the outside world. The main idea here is to keep things where effects are unobservable from the perspective of the caller in SafeIO. So data might be different each time, but the outside world didn't change except for getting slightly warmer. So IO is split into effectful and non-effectful parts, essentially input and output. So SafeIO, you could think of that as input and IO as output or writing or mutating things. We have monad lifting from SafeIO to IO, of course. We have monad dropping, so we can perform a SafeIO and get a value. And it's only SafeIO that can be both lifted and dropped. This has also allowed us to ban the use of unsafe perform IO completely from the code base. So anytime a module wants to use unsafe IO perform IO, it has to actually register that with a compiler enforced authorization. Another one is how we deal with data collections. So mu lists are actually arrays at runtime. This works reasonably well for small to moderate data sets, but lists are not our preferred collection type. A standard go-to type for collections are relations. Relations are abstract first-class objects implemented in C++, and they have pure operations on relations. You can think of relations as a tabular data structure with named columns, named and typed columns, and rows of data in the body. We don't have any material ordering of either columns or rows, and columns are only addressable by name. We have an efficient implementation of the relational operators with well-defined algebraic properties. And this makes it easy to reason about relational expressions and helps refactoring. We regularly work with relations containing millions of rows and hundreds of columns. We also have a typed version of the algebra to which we are gradually migrating. This one has a somewhat higher initial development effort, but offers savings in maintenance and reuse. So the last part here in terms of our libraries, for GUI projects, we developed a property model-based toolkit called Widget. The main feature here is that UI elements are essentially mutable properties with the user interface, and you can construct a GUI simply by building a property graph, some of them with UI, some of them without. And coupled with abstract layout, it becomes possible to write applications that are independent on how they're ultimately presented to the end user. We currently have two backends to this, one using F#.net and WPF to present what's essentially a thick Windows application to the user on a desktop. And the other one is a cross-platform service that can render applications as HTML in a web browser. So on this slide, you see screenshots of a small application using the two backends. On the left, the desktop application with a WPF front end, and on the right we have the web browser version, and they're essentially identical, apart from the superficial difference in the built-in widgets. And to show how compact this is, if we look at the code. So this page is the complete code for that application. And you can see how small that is compared to what it might have been if we had used any of the competing toolkits that have bindings to Haskell, for example, GTK or WX. And with this, we get the cross-platform browser presence for free, working both for Windows and Linux. So now let's talk about the code base overall, showing some code statistics. So the project started back in 2008 with C++ and Haskell from the get-go. And you can see that C++ and Haskell has grown in roughly constant proportions to each other throughout time. When we started this project, I projected that we would need about 1 million lines of code for a complete system, 1 million lines of C++. We haven't quite yet hit 2 million, so I think my estimate wasn't completely off the mark, and I didn't know I was going to be here for 13 years either. And in this count, I have not included the about 2 million lines of auto-generated API glue that comes out in C++, Java, and C# that is just part of our build process. That's code that is not touched by humans and code that's just thrown away after each build. Mu development started, of course, as soon as the compiler became available in early 2010. And you can see the Mu code taking off. The Mu code outnumbered Haskell code within 1 year. So the crossover there is at the end of 2010. And after 4 years of Mu development, we had Mu surpassing C++ in end of 2013. And basically since then, the Mu code base has been growing at about 500,000 lines a year. And I think when we look at this graph, we should also remember that we observe basically a factor 5 to 10 in the line count ratio between C++ and mu. So you could either multiply the mu line count here by 5 to get the kind of corresponding functionality that is actually living in mu compared to C++. So I would count that as, the mu code is worth 25 million lines of C++. Okay, the next slide here, we're just showing some statistics on Git commits and contributors. So I can see on the right side, the number of active committers continues to grow and has now surpassed 100. So we have over 100 people actively developing on the repo, which also, of course, implies that our team has been growing and continues to grow. You might wonder why there's a dip in the number of commits per month over time, kind of following 2014. Probably a couple of factors there. One is that we changed from fast forward only PRs in the integration system to be able to rebase commits already pushed. So devs are now more likely to rewrite their commits when a test fails, rather than adding new commits on top. And then also as the project is maturing, individual commits have become beefier. If you go back and look at the code trajectory on the previous page, you can see that the line count rate hasn't really been abating, at least not materially over the same time period. And then the next slide, I'm showing the distribution of module sizes. So we have over 26,000 new modules. The largest module is 74,000 lines of code, but that one is generated. Note also here that the chart is truncated on the right at 1,800 lines. So the largest modules are really far out on the right here. The largest handwritten module is just under 6,000 lines. And then we have lots of small modules with the mean length being around 200 lines and the mode even smaller at 25 lines. Again, note that the y-axis here is in log scale. And we have modules as small as 4 lines of code. They tend to be just re-exports of existing modules, kind of just pushing them under new names. Okay, so with all that new code, what are we doing to secure its future? Okay, well, for a long time, we've been considering the possibility of some convergence with GHC, at least for the front end. So this year, we started a kind of a researchy project to establish both a feasibility and kind of a course roadmap for what this would look like. So the aim now is to use GHC to compile mu to core, and then to translate core into the current mu compiler's internal representation, and then use the rest of the current pipeline and runtime. So we have to have some inversion of control in the source driver. So in GHC, you have module name resolution into file names, which are then loaded from disk. In mu, an import is either the typed interface of a C++ add-in or code from disk or service. So this we can get around simply by using a lower level GHC functions instead of the top level driver. But some GHC assumptions need to be changed. For example, string is not defined as a list of characters. So this will require patching GHC itself. And then there's some feature parity things, like we'll probably want to patch recursion pragma into GHC to retain, the discouragement, continue to discourage people from using explicit recursion. And for other things like data kinds, it would probably make sense to just migrate the new code base to what GHC provides. And then finally, as I said, the team is growing. From time to time, we have job postings. And if you're interested in applying, this slide shows you how to do it. You can go to this link and do the search as described. If you just search for Haskell, you will find jobs in other teams because we're not the only Haskellers in the bank. But if you follow the search criteria, you should find my group. And I would thank you for your interest on that. And over to Q&A.
Awesome. Thanks for the great talk, Martin. Let's give Martin a round of applause.
Thank you.
So we already have a number of questions lined up, and let me go through some of them. The first question is from Andrews. Andrews, we want to be on the stage. Okay, could you repeat this question for our YouTube audience?
Yes. So you were talking about the recursion pragma, and you were mentioning that that Mu supports these common combinators directly as C++ functions, but these are all combinators for lists or either or maybe or scanner data types. So what about user-defined data types? Version of a user-defined data types.
Yeah, we don't support that.
You don't write your own data types?
We do write our own data types. We don't write recursive data types.
I see. Okay.
Yeah.
Okay.
Yeah, we have plenty of our own data types. Of course, we're swimming in them, but we avoid doing recursive data types. When we do things that require that, we tend to do that in native Haskell and then provide that as a library that we integrate through the FFI that I say we don't have. We can write Haskell modules that become accessible in Mu. Right?
Mm-hmm.
So a good example of that would be we have the contract combinators kind of following in the same style as Simon's financial combinators paper. And actually what we've done is we implemented all of that in Haskell, and then we kind of reflect that over into the corresponding C++ constructors for all of those combinators, and then use that from Mu.
Okay, thank you.
Cool, thank you for the question, Andrews. So we have a raised hand from Philip. Philip, would you be?
Hold on. Right, what do I need to do? You can hear me. Great.
Yeah, you're very well. Hi, Philip.
Yeah, so thanks for the nice talk. This is sort of a high-level question. So I go around telling people, functional languages are widely used in finance, and that's because people need to write stuff quickly, but they need to know that it's reliable. Yes. So is that a fair thing for me to say, or should I be saying something else about why people are using functional languages in finance?
It's absolutely fair. So one of the things, I guess, we're not in the, how to say, safety critical place where people can get hurt or lose their lives, right? But we're in the safety critical place where you can easily drop large amounts of money very, very quickly when something goes wrong. And being in kind of an environment where most of what we write is purely functional, and it's sort of immune to refactoring, reordering, and so on, and you can actually understand what's going on, that's a great comfort for everybody who writes code, and we don't need to lose much sleep over things like that. So I'd say yes, that aspect of having something that is tractable and have kind of nice math semantics is really, really key for us. Another aspect of it is that we provide our environment in the end user space as well, what we call end user computing. And that means that we have people who are non-programmers who write often business critical functions, at least that they use for analysis or desk level decisions themselves. And we strongly believe that having them use a pure language leaves much less room for expensive mistakes than if they were in an imperative environment.
Right, that all aligns with the sort of stuff I say. I always feel a bit hand-wavy when I say this sort of thing, because I can say like 7 different banks use Haskell, and there are other ones that use other functional languages. But I don't really feel like I have much heft. So I guess one thing I could say is you guys have 5 million lines written in Mu. That's important.
Yes.
Are there any other statistics like that I should be waving around at people so I'm less hand wavy?
So I haven't really followed, recently what's going on at our competitors, but I know at least two other major institutions where Haskell or other functional language play a key role. And then obviously there are some funds that do it as well. But I think we're probably one of the larger.
Right. Well, thanks for a great talk. That was very interesting.
Oh, thank you so much. I think you're on mute, Ning Ning.
Sorry. Yeah, sorry. So yeah, thank you for the question, Philip. And I have already politely removed you from the stage. So our next question would be from Andrew Gundry. And Adam, would you be on like to be on the stage? And do you mind repeating the question for our YouTube audience?
Yes, I think my question's probably been answered already, which was that I was wondering whether you had support for polymorphic recursion, given that you're implementing classes with monomorphization rather than dictionary parsing. But I think you mentioned that you don't really use recursive data types at all.
Exactly.
Presumably, polymorphic recursion is also not really available. Does that impact on the kind of code you write and the kind of code you can reuse?
As I said, in practice, there's only one library I can think of, which we ended up writing, in Haskell, and then having, enough combinators exported that we could kind of manipulate those data structures from C++ and then from Mu, and that was basically the contract data type for financial contracts. That's the only example I can think of. And I guess the answer there is that yes, given enough motivation, we could work around it by simply doing that in Haskell instead. I haven't come across that type of discussion in any other context. I would say in what we do, the need doesn't come up that often.
Thank you.
Thanks.
Great, thank you for the question, Adam. Our next question is from Andrew, and then he asks, what language was the initial Mu compiler written in, and is it currently self-hosted?
Okay, so yeah, I can answer that. That's easy. So the initial, and it's still the same, Mu compiler, of course, has been evolving over the years. But yeah, it's all written in Haskell, and it's not self-hosted.
Well, that answers that. Thanks.
Great, thank you, Andrews. And Haskell, would you mind being on the stage? And the question from Haskell is, well, you can repeat it?
Sure. So you mentioned SafeIO and form safe for SafeIO going to SafeIO 8 going to 8. Did I understand you correctly that you said that reading data from the world is an example of SafeIO?
Yes, reading data from the world. Okay, but it's not reading more data from the external world. It's reading data, and then, so put it this way. In most cases, take an example, for example, reading a file. So that's in SafeIO. That reads the file and gives you the content. And if you do that again, you get the same content. It's not that you get more data the second time. Right?
So for example, like reading market data would not be an example. Is that right?
No. So reading market data, given that when you run perform, let's say in a spreadsheet, you do it as an explicit action. So it's the end user can control when that happens, right? It happens only if the user forcibly refreshes that cell, and that's because they want to have a fresh version of the data. So imagine that you have a call that is going to give you the current spot value of $yen FX, right? And it's coming back at 100.4, and you can keep hitting that cell over and over and probably get 100.4 again, unless it has moved. Well, it's going to move all the time. Next time it's going to come back at 100.5, right? But it's a user action to decide. I mean, the user expects it to move because it's live data, right? But it will only move when the user forces to perform.
I see. So because it feels like reading in a file and it doesn't change, like treating that as being morally pure makes total sense to me. But reading a market value and treating it as morally pure seems unsound to me.
I guess
that makes it not a pure language anymore, right? I have pure things that look like pure values but aren't pure values.
Okay, but reading the file and reading it again is also not a pure value if someone wrote a file in between, right?
Right. I mean, that's like a Nix, for example, right? You would like have a hash in there saying like reading with this particular context. Like there's ways around that, right? You expect it to be the same.
Okay, so here we don't expect it to be the same, right? If we expected it to be the same, we have another facility which we call the kind of the reference data service, and that's more in line with what you're asking. So things that we don't expect to move are threaded through a value that you can kind of read from purely. It's like it's kind of a long lazy read, and that's used for things like static data describing market instruments, calendars, holidays, and such, right? And that's not expected to change, and therefore, wherever you reference that in your program, it's just getting a pure value. It's like getting a constant value. Of course, from today to tomorrow, if there are corrections in that data, it will be different, but we don't consider it to be impure just because of that, right? When it comes to SafeIO, when we read from the outside world, we have to be prepared for the possibility that it will change, right? But it's a benign change. It's not like we are launching missiles or deleting files or sending out payments. We can safely redo a SafeIO as many times as we want without kind of consequence to the external world.
But for example, like 2 times perform X, is that the same as perform X plus perform X?
No.
But then we don't have you said we have a pure language, mathematical properties, but even like the most basic properties don't hold then, right?
Well, I mean, so SafeIO perform. Okay, so SafeIO perform is
Hello.
Sorry, SafeIO perform is in a monad in the SafeIO monad in mu. So you would have to use, you have to do it in a do block, and you have to actually lift it to IO if you're going to use it. The only place where we allow SafeIO perform kind of in the way that you describe it is in Excel itself. So when you write mu code, you can't just run SafeIO perform as a function, right? You have to do it in a do block.
I see. There are some like external to the type system, some external checks that limit where you can use this.
Yes. Yeah, it's actually not even exported into the. No. It's exported into the mu namespace, but it's of course it's in the SafeIO monad there. So you have to do it. You have to lift it to IO and then run it.
But the signature was perform IO of type SafeIO A to A, right? So I could call that anywhere in principle, as far as the types are concerned.
Okay, that might be a typo here. Let me see.
Monad dropping.
Yeah, I think this is only in Excel where you can do this.
I see.
I would have to go back and actually check the documentation.
I see. Okay, thank you.
Or it simply is that SafeIO perform isn't even accessible from mu.
I see. Okay, thanks.
I think we got a follow-up question from Matthias.
Okay, this is a question about serialization, I guess. Not necessarily SafeIO, but could be also. I would say the answer to this is no. because the values that you serialize in our platform are not kind of the primitive unboxed values. I mean, everything will be in some form of container with type annotations at the top. So my answer here would be no.
Does that answer your question, Matthias? We cannot hear you, so I guess the answer would be yes. So thank you for the question. Our next question is from Andrews. And Andrews, can you be on the stage?
Yes. So my question was about serialization, and in the slides you had primitive values adjust themselves when serialized, but you also mentioned that this works across different platforms and bit widths, and I assume maybe even NDNS. So I just maybe that's a different notion of primitive than what I think of, but I think of it in the GHC way where we have inserted to hash. Oh.
Okay. Yeah, I can answer that. So we, when we say that the primitive values are just themselves, so this is true with respect to one choice of a C++ or C level representation in memory. And basically when we wrote the wire protocol for the serializers, we just picked whatever was the closest to what was native to the compiler we were using at the time, and said, well, this is the wire format for this, and we picked, for example, all the word lengths for integers and so on, and the NDNS based on the platform we were, and said this is now forever the wire format. And then of course the serializers on other platforms then make the necessary adjustments to stick to that protocol.
Does that not cause issues when you have things like overflow, and so the computation might give a different result on different width platforms?
So yes, there were some restrictions with respect to the range of integers, but I think what we did was we defined ints originally to simply be 32-bit ints. 32-bit ints, and that means that when we go to 64-bit platforms, we have this extra space. We have runtime checks both ways for overflow.
Okay. So I guess in a sense you defined your primitive int to always fit into the native int of all the machines you run on.
Yeah, exactly.
Yeah. Thanks.
Thanks.
Great, thanks for your question, Andrews. I see Yamamoto has several questions. Could you be on the stage?
Hello, Gigi.
Hello, nice to meet you. Is terrical optimization supported by the Recursion programmer?
Yeah, no. Actually, if we had that, then we would probably not even have the recursion pragma, apart from kind of programming style reasons. So yeah, we don't have tail calls in the runtime, so we can't really do it.
Okay, thank you.
Thanks.
Next. Okay. Okay, next question is I. Does the HTML backend render only on the server side, no JavaScript?
Oh, I don't know the complete details of that. There will be other people here on the Yeah, there are some other people here that would know, but I actually don't have the answer. I think there might be some JavaScript in there, and I know we've been working on it, and we have work underway to improve the HTML backend to give a better user experience. And of course, in that place, I would think JavaScript or TypeScript or something like that will serve a key role, but that work is just starting.
Okay, thank you.
Thank you.
Thank you very much.
Okay, thank you for the question, Yuji. I
Yeah.
will mark this as answered.
Yes, thank you.
So, I'm turning. Okay, so just to answer Yuji's question, so the way it works is that the logic runs on the server side, and then there's this very small JavaScript shim in the browser, which just takes small fragments over the wire that update the UI in response to events. So there is JavaScript, but it's only used to change the state of the DOM, basically.
Cool. Thank you for the further clarification.
Thanks, Gergo.
Sure.
It seems we are running out of questions, and we have also reached the time limit. Yeah, so thank you again, Martin, for this great talk. I really enjoyed it, and I really appreciate you taking the time sharing the new experience with us. Yeah, you can see a lot of applause from the audience.
Well, thank you so much, and I should thank my team who helped us put all of this together, both the code base and obviously the material for these slides. Thank you.
Yeah, cool. Thank you, and thank you everyone for joining us this session. So for now, we are going to take a break, and our next session will resume in 30 minutes. So thank you, and thank you again, Martin.
Thank you. Bye-bye.